Okay, so now that we've done our processing and brought in our ground control points and our check, we can actually take a look and see how well they did. So what I'm going to do now is I'm just going to zoom in, and what we can see here is sort of if you look at this guy, this is now kind of the marriage of what the differential GPS is telling us the position for that ground control point is, and now what the pix4d model thinks it is, because it's sort of everything is shifted to bring that in line. And so we've got this really interesting situation here where we've got for uh, this three-dimensional ground control point. This is number 3, which I happen to grab here. We can see this value, which is less than 1, and that's kind of a marker that this is a good thing. And we've got some, computed positions and some error from the initial position and so on. So this gives us a sense that everything seems to be locking up. If I look at the number 2 one I did here, actually that number is a bit above 1, and which is not optimal, so I might want to sort of redo things. But if I look at my first one, that's well below 1. That's 0.4, and so that's actually quite good. So you want to be less than 1 for these different values. And in addition, you can look at the what's the term I'm looking for? The quality report, and you could go up here to process, and you could do generate quality report. I've actually already done that, but if you do that, you will get something that looks like this. It's the original quality report, right? And so the same information, except now if we look under the geolocation details, it's more informative because it's now based on our ground control point guys. And so these first 3 were the ones which were used for the three-dimensional incorporation to get to our UTM zone 5 coordinates. We look at the errors associated with these guys. And really we should have, I would say, at least twice as many ground control points as what we included in this little demo. We are only doing 4 here for demonstration purposes. 3 that were actually used for the three-dimensional ground control points, and 1 which was held out as a checkpoint. And the one which was held out as a checkpoint, this is the one where you can actually look at these numbers and interpret them and give it a little bit more credence than these ones. And what we can see here for number 4, which was held out of the calculations and only being used as a check, is that the error in the x direction is about 2 centimeters. The error in the y direction is about 3 centimeters. So that's actually fantastic, because at the height that we were flying, we were expecting about 3 centimeter per pixel, and so we're in the range of 1 pixel error, which is quite good. Our z error is not so good. Actually, our z error is 13 centimeters, so that's quite a bit off. But again, it depends on what your concern with is in terms of vertical. Vertical is often more problematic, and so if we had more ground control points, we could maybe beat this down. But this is a true representation for at least this one checkpoint. It'd be much better to have 3 or 4 checkpoints and then actually get the average of their x, y, or z errors. But this is what we've got. So now we've got some confidence. If we keep scrolling down here, we can see for the individual ground control points, there's information about each of these ones, and it wasn't marked. And anyway, it just gives you a sense about more information about how this is working and how it all sort of checked out. So I'm quite pleased with what we've got at this step, and the next one is to move on to the point cloud densification. So we're going to let that guy rip, and we will actually, I'm going to undo the initial processing because we're just going to do the point cloud densification. We're going to go ahead and start it, and then we're going to see what we get in that case. And so this is going to take some time, and that's just how it goes because we're dealing with lots of information and lots of data.